So, how do we get that?
Yeah,
Here. Yep.
Need help. Where is your talk?
It's SL, this one. So, all right.
Where does it start? Slideshow.
Play from start. There, yeah. Okay, perfect. Thank you. All right, so this is the title of my talk. Oh, I will take a couple of minutes to relate to a discussion that happened last week, and I'm sorry I have to say that. That's for the diversity person here was Alexei. So last week there was this, this is a brief diversion. I don't think they're taking this stuff. There was this tensor charge, and this is what I call it, and the Strumia effect. So there was this discussion at dinner. Now, Eke always leaves at my talks, and she misses the fun. So, with Aurora, together with Aurora, this is a paper with 2 women. Okay, we published this paper, which is the first paper ever to have evaluated so we stuck our neck out in this paper to have evaluated the impact of the experimental tensor charge, okay, on destruction of BSM type elementary tensor interactions. So we wrote this with Stefan Bassler at UVA, experimentalists, and so on. And so this paper was never quoted at the INT talk on week 2nd on the tensor charge. And so this paper should have been quoted. And then the person that was not quoting this paper was agreeing with Strumia that women don't get they get hired even if they have so few citations. Well, if you don't quote them, how are they going to get the citations? So that was the one remark. And
you guys know what this Strumia effect?
Yes, I know what it is, but I don't understand what was missing from the
last.
Yeah. So can you be more specific here?
Yes. So, well,
was it Aurora who didn't want her results?
No, Aurora did not talk about this. There was another person that talked about this, and she never quoted her in my paper. He never quoted hers and my paper. And then at dinner was arguing about, that in favor of the Strumia thing. So if you don't quote us, then that's what it is. And so I had some 2 hours conversation with Aurora on the phone. So this is the result. Anyway, this was the diversion. So you can look more so on that page. There's going to be online. And I'm sorry, but sometimes the record has to be set straight. So since I saw that there is a diversity person, I just took. Thank you.
I'll have a conversation with the person who was it.
Very good. Thank you.
That was in the next year, probably. Can you show me your first slide, please?
Now that was in this year program.
No, the first slide.
They're invited.
How did I do that? Yes, I want to give this talk in the, what? Okay. So anyway, I'm going to talk about.
Alexei will not be the diversity.
You're fired. Okay. So anyway, I'm going to talk about gravitational waves. Who knows if there's something that boosts us in the future. So this is the outline. I'm going to briefly go over the physics goals, theory, and then method. And disentangling, I'll talk a little bit about disentangling quarking gluon orbit angular momentum. And there are going to be 2 talks by Brandon Kristen on Twisted GPDS on Thursday, and looking at the cross section. So this is relevant for what Matthias, the concluding part of Matthias' talk, and then Abba's talk on Thursday on the sum rules. All right. So all this program also can be explored at the Center for Nuclear Cryptography that has just been created at Jefferson Lab, and this is important in this context. So the physics rules, we all know them. I feel like I have to go fast because I see the time. running. So, so GPDs, I think, are a new paradigm that will allow us to both penetrate and visualize the deep structure of visible matter and to answer questions that couldn't even afford asking before, with all the, the intricacies that they come with. That's part of the story. And so, we are interested in what, the distribution of the force and pressure of mass, and the force and pressure inside the nucleon is, and I'm going to talk about this. And again, the other topic is, so on one side we're looking at those moments of the energy momentum tensor, and on the other side we are looking at the Fourier transforms, the 2D Fourier transforms that have generated these diagrams that we all know and love. All right, so and the way to see this is that GPDs connect to the complex phase distributions. This is to phrase it in a more general sense. And so the important thing, I think, the impact that GPDs will have in general is that to observe, evaluate, and interpret the linear distributions will require stepping up the data analysis. Okay, and so there's going to be a brand new effort that goes beyond, okay, what we've been looking at now, in which numerical, analytic, and quantum computing methods are going to come together. Okay, so this was my brief introduction. So now, the energy momentum tensor. So how does the proton get its mass and spin? So we know this is the Lagrangian, and you know that by imposing invariance of the Lagrangian translation and rotations, we define the energy momentum tensor that looks like this, and under rotations, we have to form a slightly more complicated tensor, which is the angular momentum tensor, and this brings us back to our classical quantum field theory notions. All right. Only now we're looking at that. We're replacing ENM with QCD. So that's the energy momentum tensor, as we know it. So just to define a little bit things, we have the energy density, the momentum is on the sides, and here are the shear forces and pressure along the diagonal. And again, as we have seen it defined in our classical theory studies. Okay, so the conserved quantities here are momentum that we define in this way, and angular momentum that we define in this way. So it is important to go over the definitions. That's why I'm doing it. So now for a spin zero. So now we take this energy momentum tensor and we parameterize it. So we parameterize it for a spin zero system. So I haven't said QCD at this point. Okay, so this is just the energy momentum tensor for a spin zero system. And we parameterize it in terms of 3 form factors. So 2 conserved plus an extra non-conserved, not separately conserved. This is where where the QCD enters in this part for quarks and gluons. And for spin 1/2, we know that there are 3 form factors, and these 3 form factors which are conserved, and a form factor which is not separately conserved, which we call CT. So we've seen a lot of this morning, so I'm not gonna say a whole lot of it. Now, I like to also mention the deuteron because it's something that I think is important, something that I care about, and it gives us a whole lot more information. So for the deuteron, if you count the form factors, and there is a way of counting the form factors that I'm not mentioning here through the JPC quantum numbers in the T channel. So we know exactly that there have to be 3 for spin 1/2 and 7 for spin 1. These are the other form factors. And this is cool because sorry, let me get back to this, because it gives us other, through the different unicity structures, we get a whole lot of information on the charge and on the quadrupole also of distribution, which characterizes it. Okay. So, okay, this is the momentum. We can form these relations. So the momentum relation, the angular momentum relation that we've seen again this morning. This is why I'm really zooming through. And for the IJ part, okay, the spatial part of the stress tensor, we can also define, okay, this form factor C and this relation that is describing the stresses, the forces inside the nucleus. So we can map it all out. So now, how this was the energy momentum tensor. So how do GPDs enter in this picture? GPDs enter because, as again, you've seen this morning. So back then, Jaffe, Manohar, and G, they both saw that there was, an off-forward part of in that energy momentum tensor. So they knew that there had to be an off-forward part. So then G went one step forward, and he noticed that for the quark and gluon operators, if we define the angular momentum like this, the moments, okay, so the moments of this correlator, so the local operators, coincides with the ones for a specific correlation function at z equals 0. So there is a coincidence in the moments for the energy momentum tensor and the GPD matrix elements. This is just based on this coincidence that we can explore the energy momentum tensor matrix elements through deep virtual contour scattering. And this should be clear again to this audience. So, okay, so then, we can, since this is an integrated NKT quantity, you can form, you can use the operator for the expansion. The only thing that changes is that the external momenta of the external momenta are different, okay? The external momenta that are involved, and so we have the helicity, for instance, for the gamma mu for the vector operator, we have the helicity conservative and helicity flip operator, and we form the Manning moments. We are interested now in the second Manning moments, and the second Manning moments, there is exactly this coincidence from, if we write them from the operator from the structure point of view and from the energy momentum point of view. This C that appears here in C20 is also called the D term. So from this, we understand the GPDs and these deep virtual exclusive experiments are key to interpret the mechanical properties of the proton and of the deuteron. Okay? And the deuteron has this interesting feature that we get two D term things. And so what are these two D terms? Okay, this is up to interpretations. So, okay, where are we now? So this is out of one of Marta's presentations. This is for t equals 0. This is just to summarize the situation. So we have the A matrix elements, A plus B, that we can also have an experiment somehow. This is from an experiment on the neutron back then at Jefferson Lab. And then the calculations of Marta as well are consistent with the calculations of Keife and others, and then LHPC, which is represented here. And they go on, and they are consistent with these experimental determinations. These are experimental determinations that have a lot of theoretical input in it, so they're model-dependent experimental determinations, because experimental determinations, even with the model dependence, they have a big error. Let's focus on C. So C, again, it was calculated in the lattice long ago, and this is now summarized. This was calculated before 2011, but it was summarized. This is the most recent slide I found on these on this form factor from the horse's mouth here, and C is this green part. We can have the U minus D and the U plus D combination, and recently the D term, okay, which should correspond to C, was also measured in experiments. And this is out of the Nature paper by Burker, El-Adreri, and Giro. So this is C versus C inside the proton with the parameterization. And okay, so this is now, so we started looking at these calculations, and this is what, when we started doing Fourier transforms, this is why T here in this graph extends to very large T, but really the region that we're interested in and that overlaps with these other ones is the one in this rectangle.
Excuse me, can I ask you a question?
Yeah.
I suppose the lattice calculation in those things are just connected circuit that got included.
Oh yeah, this is LHPC back then. Yes, yeah. So that's why I find that yeah, this is why it is timely to. But this is all that is available. Okay.
What is the experiment?
This one here, oopsie. Sorry.
But I think there's.
This one here, you mean?
No, no, right.
The right one.
No.
The right,
The green.
the green curve is this. We took this with the, there's a factor, 4/5 or 5/4 times the mass. But it's exactly this, in these units, yeah.
I think Jenna had that one we have calculated the term varies last week, but I don't remember. I don't know whether they included the disconnectors, right?
Okay,
We
so
can look at that.
so if we want to compare with the experiment, if this is, well, compare with the experiment, that should definitely
It's
be.
hard to compare. They're vast
That
connections, but it's just newer.
Again, yes, I'm going to quote some of their stuff that they did, but again, not this. So now, what I want to come to, the point that I want to make here, this is a new point of view. So, besides looking at deeply virtual exclusive experiments, all types of experiments, DBCS, TCS, and so on and so forth, it is important to look at, to include, now we're in a moment where we can include data from neutron stars and gravitational waves. And so we can use really neutron stars as a laboratory for testing QCD, and our analysis and global analysis should include this data just as well. Whatever we find in our experiments should be consistent with what we find in these experiments. And so what we did recently, this was recently, we started a few months ago with Alba before she moved to Brookhaven and started. We've been comparing, the QCD energy momentum tensor with the equation of state on neutron stars. We try to make a connection, and this is what I'm going to talk about in the next 10 minutes. And probably I'll just limit myself to that, and so that we can all have lunch, unless questions come, or I'll show things in the discussion. So anyway, so the event GW1787 is an important event. This is the observation of gravitational waves by Virgo also, and electromagnetic waves, or gamma bursts, from this binary neutron star merger that I depicted here, and that you probably have seen many times too. So, so now the candidate nuclear matter equations of state must satisfy the constraints on the tidal deformation of neutron stars that comes from this GW17-0817 event. And I'm going to show you what I mean specifically. So, okay, in general relativity, so the EMT is the source of the gravitational field. So we get an action. So this action here has two pieces, a part which is which has the Lagrangian that is going to connect to our EMT, and a part that describes the curvature, okay? And the metric, the determinant of the metric tensor is here. This is just, I guess it's almost general relativity 101. This is where our team union comes in. So then there are common the TOV equations, Oppenheimer-Volkoff equations, and these equations relate the pressure, the energy density, and the number, what I will call the number density, the mass density inside the neutron stars. And on the top of that, we have, so what is important for the TOV equations, if the TOV equations, is the equation of state, okay, for nuclear matter that relates pressure and density. So all of this has to be taken into account together. Now, let's think about it. I know that's late. I feel bad. Let's think about it. It's okay. Yeah. Let's think about it. So, so I've been defining the EMT, and we probably saw that talk on the EMT many times, and you were like, oh, well, okay. But I mentioned in there exactly energy density or momentum density. I'm going to get to that in a moment. I mentioned where there's a density, we know that there's a number density that we deal with, which is the moment A10, right? For lattice notation. And there is a pressure density. So all of these guys are here. So we can play the game. That's what Abba and I thought. So, okay. And so this is important because once we solve these, this goes into the mass radius relations, and this is very, very important for these observations. And I think that we should, as a community, make the connection. So that's why I stuck my neck out. I'm good at that. So, okay. So in other words, we can look at constraints from the equation of state of neutron stars on high energy, deeply virtually exclusive experiments, as well as constraints on the equation of state of neutron stars from high energy, deeply virtually exclusive experiments. We can look at it both ways, okay? The two sets of experimental values.
I don't see any connection between because you're talking about the single nucleon property. But the equation of state for the nucleon.
Yes.
That's
yes.
minimal effect of the nuclear matter. So
right.
I don't see any connection.
No. So that is a very good question that I've been asking myself at the beginning. But then, well, think about it here. This is look at this. We can talk more later, but think about there is translational bias. So we're looking at when we think about the neutron stars. I'm not looking at the neutron star is 12 kilometers big, right? So I'm not looking at an object that is at all the structure of an object is 12 kilometers big. I'm looking at the microscopic structure. But clearly, if you think about how this is just the Ravenov versus this black curve here, which was a standard nuclear matter calculation. When you think about standard nuclear matter, you're thinking about protons and neutrons in the nucleus, and then you can extend your model to infinite nuclear matter. But what you're looking at is at the microscopic level, and what determines the P versus E, so the equation of state diagram is what happens at the microscopic level. And the same way you can put nuclear matter here, you can look at quark matter, and this is what these guys in the various color curves have been doing using quark models. My point here is, let's not use quark models. Let's go directly to the EMT, to the energy momentum tensor of QCD. So if you're not okay with putting on the pressure versus energy diagram the quark model evaluations, then that's your point. If you okay this, yeah.
Sorry, I think what I hear you saying is that, say, at the very high density, if you have a core of a neutron star.
So we're looking at this part.
Right. So, well, and it should be a sufficiently massive neutron star.
Right.
Then, of course, you may have, this has been suggested, you may have quark matter there, and it will be a quark equilibrated, finite, but very low temperature, non-zero baryochemical potential.
This is from my collaborator Katiagi, UVA.
No, I'm not questioning her.
So this is equal zero.
Understand what Yoshi was asking a bit better, right? So on the one hand, in the neutron star, we have finite mu B, practically zero temperature quark matter.
Yes.
And now, the only thing I can relate to what goes on inside the proton is if you say that the proton is essentially just a ball of quark gluon plasma.
Right. No, not quark gluon plasma. We don't have to go to quark gluon plasma.
We do because it's we have a thermal distribution.
Well, we are okay. What convinced me here is that you can make this. Well, that is the way. That is one way to go. But that is you can look at it at finite as a system that has finite temperature. But you can look at it also at T equals zero. And so this is where we are.
But there's a finite
mu,
so you still have a distribution.
Sorry.
Finite mu.
There is a finite mu. Yes, and the finite mu is what regulates the transition from nuclear matter to quark matter. So there is a finite mu, and that is important, and it's what on these curves described. I think it's important for this transition. So we can include that too. That is what's going to regulate that nuclear matter is here, quark models are here, because there is a finite mu. Then there is a transition that happens sometimes. But nobody. This is the nobody prevents you to look at the core. I mean. Of the neutron star as through the energy momentum test. If you can model it if you can put a quark models calculation in there, you can put at T equals zero. Why not go directly to QCD? That was it. So okay. So we started, but yes, I have been puzzling over this myself because it was attractive to me, but. I had the same questions 2 months ago. And so So we started looking at stuff, and indeed, you know, you can plot the pressure versus energy density, and compare to what is found in this AP4 curve. And so this is what comes out of a preliminary calculation. Yes, I'm saying preliminary so that I get her off the hook. so okay. And okay. So then, and then we can move on. Okay, we can try to make the matching of the various quantities, the densities, and so on, and pressures with what we have for the quarks and for the gluons sector. The gluons, oh yeah, the gluons, we recently got them from, in fact, I knew about the C20, that's right, sorry, you could have said that. Yes, I knew about the C20 because we used it to calculate this matrix. So, it's lattice, that's only lattice, yes. So, okay, so we calculate everything. We can calculate everything and then figure out, this was mostly Kent, consistency checks. So whether there's causality, whether our calculations obey causality, and there's a causality relation that is here. So the speed of the sound in light, this is upside down, but the speed of the sound in has to be always smaller than the speed of light in the medium, and this our results obey causality. There is a first law of thermodynamics, and so the first law of thermodynamics, which is just conservation of energy, and so we take it at equals 0, and here we have, it involves pressure, energy, and density, and we have, if you look at the quark sector only, we're not completely consistent, but okay, and then there is the energy density versus number density that goes straight on to the Pandari-Pandey calculation, and that is making me wonder a little bit. However, this is how we compare. And so, so the gravitational waves / neutron stars data have us raising once more questions on some outstanding problems and in a new perspective. So, is the gravitational, the GR, the general relativity EMT, the QCD EMT, so for internal consistency of the theory, the GR EMT is symmetric, right? So how do we deal with the antisymmetric terms that we know that appear in our EMT? As was raised, this point was raised back then by Becker, Lieder, and Truman, and then Cedric Lorset pointed that out again. Again, we have to put the mass energy density in QCD, and we have to, really straighten out the role of gluons. And then finally, we have the interpretation of forces that comes in, big time when we look at the pressure term. So I have that for you. so this is out of actually Yibo Yang's one of Yibo Yang's presentations. So we can do this decomposition, and we've heard it a lot this morning. And so, we have a quark energy, a gluon field energy, and then the part that comes from the trace anomaly, as G pointed out long ago. Oops, sorry, this slide shouldn't be there. This is about, okay, you can do this game in the neutron just as well, okay? But it's, okay. So in other words, so what needs to be calculated? Let me go back to this. So what needs to be calculated, what we need to know is these terms. So these terms that we calculate will give us the energy in the end, are all of these terms, and we can put that in our energy momentum tensor, but we need to have, in order to play that game, we need to be able to do the Fourier transforms, so we need the t-dependence. That's why I was asking this morning about the t-dependence, and this will be important to get this out. So I could almost conclude here, because the rest of this talk is going to be on femtography, so on topics that Brandon and Abba are going to talk about. So, so this is, okay. Facing the next challenge is we're going to do images of the nucleon at the femtoscale, 5 orders of magnitude below the images that we see from studies of nanostructures, right? And below. Again, as Matthias has said, we know that there is a the proton relativistic wave function obeys Poincare invariance, and this has brought up, surprises. And we know that for instance, if you look at so you can map out faithfully the spatial quark distribution in the transverse plane, and by doing that, this brought up this surprise that is over here, that is telling us that if you map out this, if you look at the quark structure of the neutron, the negative charge sits in the middle, because this is where the d quarks are, and the positive charge is on the outside, as opposed to our textbook picture, okay, in which the negative charge was, the neutron is seen as a proton surrounded by some negative ions, okay. And so, okay, so we can so the important thing to understand here is there are two distinct scales, and that we play with them. One is the Yoffe time that we have seen yesterday and again today, and the other one is the distance. It is the Fourier conjugate of the momentum transfer between P and P prime. So GPDs are interesting, in my opinion, because they involve these two types of distances. So there's a next distribution, which is a Fourier transform of one body, if you want to use that terminology, non-diagonal, in many-body theory, non-diagonal density distribution in the Yoffe time. And at the same time, it is the delta distribution gives us a Fourier transform of this, again, one body, diagonal density distribution in B. And by using these properties, we can make models of GPDs and map them out. Now, as I said, I will stop here. So there is an important thing that connects to Matthias's talk, and unfortunately, it is based on these two published papers. But unfortunately, I won't have time to talk about it. And so we found out so this is the definition of angular momentum, orbital angular momentum, as Matthias was talking about before. So it's the integral of this GTMB. So now, one recommendation that I have is that we should stick, this is, I hope you agree, Matthias, you have Mark Schlegel right there. We should stick to that paper, to the Meissner-Metz-Schlegel paper, because they classified the whole shebang, basically, and they give us a way of understanding, of pointing out which helicity content goes in which GPD, and the helicity content might be the reason why these cancellations of that you are pointing at occur, and so that makes it much easier. So anyway, so we stick to that paper, and the notation is ugly but efficient. So F14 is the one distribution GTMD that describes orbital angular momentum. So the question was, can it be measured? And I found a little while ago, and she's going to elaborate on this, that indeed it connects through, this is what I define a Lorentz invariant relation. Okay, so this is a Lorentz invariant relation. It connects an integral in KT squared with a twist 3 GPD. So an integral in KT squared of a twist 2 GTMD to a twist 3 GPD. And this is like the extension to the all-forward case of the Lorentz invariant relations that we have seen, otherwise. So yes, so this is the connection that we can make. So while it's kind of hard to go after this one, you can try. And in fact, Yoshida has tried, and other people have proposed something to measure these. And it's important that we go and try to measure these. This one has also its interesting features, okay? And okay. So, all right. I have a lot of slides, and I won't go over them. Let me just skip to the very end. And yeah, this was to the very end. There should be So how do we observe all this? It should be a multi-process, multi-variable analysis, and I think that this workshop is also about it. So not just deep universal Compton scattering, but time-like Compton scattering that allows us to, in fact, test universality, and so on and so forth. All these processes should be taken into account. Yes, and this will allow us to map out GPDs. For this, we need a formalism, and the formalism that we've been writing. So there isn't a unified formalism for GPDs, and Brandon and collaborators will be writing the formalism, and this is a little bit how it looks like, and Brandon will talk about this. Let me conclude by saying that this is my wishful thinking, okay, although Matthias has put a lot of, because we are able to describe the orbital ornamental as a GPD, you know, I think that it can be disentangled from data in an easier way. And you know, more on this probably in the discussion this afternoon. And so in order to detect all this, we badly need this collaboration. And I am announcing, that's my conclusion, this UVA symposium on imaging and visualization that is happening on December 10 and 11. So this is a preliminary version of the poster, and there's a webpage, and this is just it's a Virginia effort, so it's funded by, you know, the governor, and we have been asked to organize it at UVA, and so we'll you know, just get in touch with me if you know, are interested in coming. That's all. Thank you. I kept hello.
Thank you. Any questions? Yes. Yes.
Could you please go back to slide 41?
Yeah.
When I look at that equation, on the left-hand side, there's some TMD that potentially depends on Wilson, choice of Wilson.
Oh, yeah.
On the right-hand side, I have GPDs, which are presumably defined in terms of like local manifestation variant operators.
Yes.
No Wilson line.
No. This is the G version of that.
So it's for straight Wilson line.
Yes, I can give. Yes, I can give. I have a whole discussion that I skipped and that Abba can talk about. Right? Yes. Yeah. Or you won't. In any case, we can write this. So this is the G version, and so that term, the top term, is put to 0 here. It's equal to 0. You can do it also for for the torque, not different from 0. So there's another term that is the torque term that enters in here. But this was for the purpose of just presenting this equivalence. So I didn't go into fine detail. But of course there is all that, and that's in the paper.
I'm just curious about one of your statements. You said there is no unified formalism for GPDs. During the first week, my impression of the discussion was that actually people were saying, yes, we do have unified formalism for GPDs. So in what sense there is no?
No. Okay. So yes, thank you. I need to clarify what I was. So for GPD, so there is one paper, and this paper classifies everything by Meissner, Metz, and Schlegel. And in this one paper, they do not look at phenomenology. They just look at the correlation functions. And so they have the off-forward correlation functions as you go down layers of integrations in the quarks momenta. So you have the integrated over K minus only piece, which gives you the GTMDs. You start even before that, okay? You have the complete and integrated piece, and then you go down, and they give you the integrated in K minus piece, and this gives you all the GTMDs. And they did all the GTMDs for all the operators, possible, imaginable. So they have them all. Yes. Then they integrate, and you can integrate. So you can go to the forward limit and get all of the TMDs, and they write there all the TMDs, and then you can integrate in KT, and you have all of the GPDs, all of them up to TWIS4. So they have, that paper is complete. We used it a lot. Yes. So although, well, okay, with some caveats, yes. So okay. So that is the GPDs. So for the GPDs, we should stick to that because that exists. And now I know, so like, for instance, I know this E2T3, I know where it's coming from. I know that this one is from the vector sector, TWIS3, and by looking at that paper, this is TWIS3 vector sector, and it corresponds to longitudinal proton polarization. Okay, and so on and so forth. We can do the same as what you have been doing for the TMDs. For this, we have it. What is not in place, and what we've been painstakingly working at, and I spent, we spent, yes, afternoons and afternoons, and Brandon more than me actually, is the formalism for the exclusive reactions. So in the exclusive reactions, this thingy here that I'm showing you, this formula, big formula, oopsie, this is our formula. This is from our paper, and it's so in which you can see, it reminds you of the TMDs, right? So there is a UUT term, unpolarized beam, unpolarized target, unpolarized beam, unpolarized target with cos phi modulation. Then you can polarize the beam, you can polarize the target, and so on and so forth. So this has in the numerous papers that have been written in the past, this type of pointing out, this type of helicity-based, helicity amplitude-based analysis had not been done. Strangely, even if they call their paper, there's some papers, very skillful papers, helicity amplitude, but it's hard to penetrate. Okay. So instead, this makes the connection between this and the various correlators. So that is what I was saying.
For each of the objects here, they do have a clear interpretation in terms of
techniques. Brandon's going to talk about it. Oh. Let me just say that. I won't steal his talk. Yeah.
Any other questions? If not, this is our speaker. To remind you, we will have a discussion in this room at 2:30.
Not normally they are in the other.
Here, we checked. This room is available for the whole day. We have to come back. So here, so there will be a few slides. You have some slides you want to show us? Please go ahead. Something. Great. Great. See you at 2:30. So, you have something?
I'm thinking about Jennifer.